Hello again. In the last video, we have learned about the new concept that is called continuous compounding, and we were assuming that at every moment throughout a year, the interest in a savings account is compounded here. So we have calculated the continuous compounding compound amount factors respectively for each compound amount factor that we have learned earlier. So we have converted the single payment compound amount factor or the single payment present worth factor for the uniform series compound amount factors and the gradient series compound amount factors one by one to continuous compounding case. Now, up to this point, the problems that we have solved, the compounding was occurring continuously. However, the payments were made at annual time point. So only end of the year payments were considered in the problems. Now we are just going to consider again discrete payments. However, this time the payments are going to be made in different periods than years. So let's just say in case where we have a monthly periodic payment, how are we going to solve continuous compounding problems? Actually, the procedure is easy. Let's just say the interest compounds continuously, but the payments are made p times a year at equidistant time intervals. For example, if the payments are made monthly under continuous compounding, then this p is just going to be taken as 12 because there are 12 months in a year. In that case, in all compounding factors, in all continuous compounding factors, the annual continuous compounding interest rate should be replaced with R over P, which corresponds to the continuous compounding interest rate per period, okay, per payment period. So basically, by dividing the nominal interest rate again to the payment periods, number of payment periods in a year, we will calculate the compounding rate for that payment period. So it is just going to be called continuous compounding interest rate for a single payment period. And of course, if the payments are made in these periods, then we need to count the number of payments that are made in the investment horizon. If the investment horizon consists of n years, and in each year p payments are being made, in that case, in total of n times p payments will be made in these investment horizon. So all continuous compounding compound factors are going to be replaced with the interest rate that corresponds to the payment period, which is R over P, and the number of payment periods will be replaced with n times p. The number of years will be replaced with the number of payment periods. Now, let's solve this question to get this better. A person borrows $5,000 for 3 years to be repaid in 36 equal monthly installments. The interest rate is 10% per year compounded continuously. Again, in this question, we are mentioned about the nominal interest rate because it says per year, and because the compounding occurs in a different period than year, in fact, the compounding occurs continuously, and we understand that we can use this as the nominal interest rate per year as R, and we are just going to solve our question with the compound amount factors obtained from the second table, or we are just going to use the continuous compounding formulas. So the person borrows $5,000 for 3 years to be repaid in 36 equal monthly installments. So this means what? This initial amount, this principal amount borrowed right now from that bank, and it is just going to be repaid in 36 months. 36 months. So the payment periods are different than years. So what we are going to do in the question asks how much money must be repaid at the end of each month. So what are our installments, monthly installment sizes, if we want to cover our whole debt of $5,000 in 36 months? How much money should we repay at each month, the question asks us the recovery amount. So we are going to use the capital recovery factor, of course. However, in this question, we need to assume the nominal interest rate as 0.10 as decimal. And since the number of payments made in a year is 12, the monthly interest is going to be 0.10 divided by 12, which is R over P. So this is our monthly interest. And then instead of the number of years, we are going to replace it with the number of payment periods, which is 3 times 12, which is 36. Now, if you want to identify the monthly installment amount A, then we need to multiply the principal amount with the capital recovery factor A over P. Now, if you check our previous pages, the A over P uniform series capital recovery factor is defined as e to the power r minus 1 divided by 1 minus e to the power minus r times n. Now, this formula is only valid for yearly payments, but in monthly payments case, we need to replace the annual interest rate with the payment period's interest rate, which is r over p, and here the same will be done. So this r will also be replaced with r over p, and here n will be replaced by p times n, number of the payment periods. Of course, if you do this operation, the p values will cancel out again in the denominator of the formulation. You will see r times n. In fact, in this solution, you see we have e to the power r over p here, and we have r over p and n times p here, where p's will cancel out. Again, we are just going to multiply r with n. Now, you see here we have 0.10 times 3, and we have 0.10 divided by 12 here. Of course, for such a periodic interest amount, so 0.10 divided by 12, it's not a value of interest that we can see in our compound tables. So either you would use a linear interpolation between the closest interest rates, or what you can do is simply, instead of doing that, you can directly use the formulation here. Of course, you need to definitely know how to calculate exponential functions using your scientific calculators. So in that case, under this continuous compounding, the monthly installment amount should be $161.43, so the person can cover the debt in 36 equal monthly installments. In the end of the 36 payments, all debt will be covered. Now, this time, we are going to move to another topic, but we are going to study this in this next video.